picture, a screenshot, and minimize this so I can write. All right. It is, I'll write over here on the right. The temperature, hold on, I may have to read this further to know what, yeah, capital T is temperature as a function of time, is what that means. The temperature as a function of time is equal to the temperature of the medium plus the temperature initially minus the temperature of the medium to the e to the minus kt. And sure, and I run out of paper. T, the medium, plus the original temperature minus the medium times e to the minus kt. So that's his law of cooling. T sub m being the temperature of the surrounding medium, T sub O being the initial temperature of the object. So what we need to do is calculate K. In other words, if we want a specific equation for this pizza, then it's going to have its own K. Okay, K is a constant. And so I can calculate K by filling in everything I know and solving for K. Okay, so pizza baked at 450, that's its initial temperature.
Okay.
That's where the 450 goes. Moved from the oven at 5 p.m. into a room that's a constant 70 degrees. And after 5 minutes, the pizza is 300 degrees. When e to the minus k5 at what time can you begin eating the pizza if you want its temperature to be 135 degrees? Well, we have to solve for K. Once we solve for K, we'll have the specific equation, and then we can put in a whole bunch of different, I can put in 135 for this, and that will allow me to solve for T. Okay, so the first thing let's do is solve for K. So we have 300. Tell me how to solve for K. What's the rest of it? Help me finish this equation.
So starting it off, I would subtract the 70.
Okay, so, well, let's simplify a little bit, because these are just numbers, so that becomes 380 times e to the minus k5. Okay, so if you subtract the 70, you now have 230. And now I'm going to divide by 380, right? To get rid of that. And so here's what I have. I have 230 over 380. Get rid of that 0. Equals e to the minus 5k. I'm going to put the coefficient in front. Now, how do I solve that for K?
Can't we take or do you get the real number for the 3?
No, you're right. You want to use logs. In other words, whenever you're solving for a variable that's in the exponent, you have to use logs pretty much every time. So I want to take the log of both sides, and the best one to use is natural log because I'm dealing with e. Okay. Now I can apply the rules of logs. So what's the right side of the equation look like when I bring my variable and exponent down on the algebra line? So here's the left side. The right side look like?
Just minus k times 5.
Right, minus k times 5, because natural log of e is 1. So that goes away. So k is equal to all of that divided by 5. By minus 5, rather. And that is going to be a negative numerator. You have your calculator in front of you?
Yeah, I do.
Let's go ahead and come up with a number on that. You don't necessarily have to. In other words, I could substitute that in for k into my equation and would be perfectly fine. And I could continue to solve it. In other words, I can leave an exact answer, but it makes it awfully messy looking when you do that.
Yeah.
I'd rather come up with a k that's a number. What do we got for k?
I got negative 0.1.
Okay, the numerator, do the numerator alone. What do you get for natural log of 23 over 38?
I got negative 0.5.
Okay, so negative 0.5 divided by negative 5 is a positive 1. Correct?
Would it be divided by negative 5?
Do the natural log parentheses 23 over 38. Make sure that the 23 over 38 is all inside the parentheses.
Wouldn't it be negative k times 5 though?
Well, I got rid of the negative 5 by dividing both sides by negative 5.
Okay.
And I know the numerator is negative, and you said this was minus 0.5?
Yeah.
And divided by minus 5 is plus 1/10. Not 1, but 1/10. Right? 0.5 divided by 5 is 1/10.
I got negative 0.1. So.
Well, I get a positive because the numerator is negative and the denominator is negative.
Oh, I didn't have a negative denominator.
Well, here's the thing. This is a negative k up here in the original general equation.
Yeah.
And so when I come up with a positive k, that's fine, because I'm going to stick that 0.1 in for k. I came up with a positive 0.1. Well, the negative sign is still there.
Okay. Because it's just negative k.
Yeah.
Okay.
In other words, because they call it negative k, I'm normally going to come up with a positive number for k, because this thing is always cooling. So I would expect that negative k to always be a negative. In other words, I would always expect a positive k. Now, at what time can you begin? When can you eat it if it has to go to 135? Well, here's my equation. It's now negative 0.1 t. And over here on the left, we're wanting it to go to 135, which is where we can eat it. So now we solve this equation. Is it too messy for you to see what I'm doing, or?
Kind of.
Okay, let me erase some stuff over here on the right so that I can rewrite it all. Okay, we've got a k. Actually, that k was pretty exact. When you did the log of that numerator, it came out exactly minus 0.5.
Minus 0.502.
Oh, okay. So it wasn't, okay. So
Wasn't,
we've
yeah.
rounded off a little bit.
Mhm.
Okay. So here's my equation right there for this pizza.
Yes.
Okay. Wouldn't necessarily be the same equation for a different pizza. A thicker crust might take longer to cool. So it might have a different K. But if my K is 0.1, then I got to solve this problem. I got to do 135 as the temperature I want the pizza to get to so I can eat it, equals 70 plus 380 e to the minus 0.1 t. And that's the equation we have to solve. And we're going to solve it basically the same way. We're going to move these two numbers out of there, and then we're going to take the natural log of both sides. And what's that give us? That gives us 65 divided by 380 equals e to the negative 0.1 t. And we're solving for t, so we take the natural log of both sides. And again, t is going to be this divided by negative 0.1.
Mhm.
So what is that? What's the natural log of 65 over 380, and then take that and divide it by 0.1? You can leave the negative out if you want.
I got negative 17.6578.
17.65. I know it's a positive number because that numerator is negative. Whenever you take the log of a number between 0 and 1, your answer
Oh,
is
I just divide it by a negative 0.1. Yeah, so
right.
it has to be positive. Yeah.
So t is positive, and t has to be positive. If you get a negative t, something's seriously wrong because you can't go backwards in time. So in 17 minutes from the time you take it out of the oven, it's going to be down to 135 degrees. Well, at what time can you begin eating the pizza? I guess at 5:17
Yeah.
or 5:18 maybe, if they want you to round that off.
Okay, or just wait an extra minute just to be safe.
Yeah, really. Okay, what else are they asking here? Use a graphing calculator or use a utility to graph the relationship between temperature and time. Well, there's our relationship between temperature and time.
It's just going to go down over time.
Right. Do you know how to do that on your graphing utility? You have a Inspire, right?
Yes.
That should be relatively easy to put into there.
Mm-hmm.
Let me think for a second. You don't want to put it in like this. In other words, we can only have one variable, and that's got to be it. Right there, the t. So I guess you'd want to put it into your calculator as the temperature as a function of time is going to be equal to 70 plus 380 times e to the minus 0.1 t.
Mm-hmm.
So that's what I would put into the calculator, and it'll be able to graph that. Got one variable only, t. Okay, so that accomplishes B. Use intersect to determine the time that needs to elapse before the pizza is 160. How are you going to do that on your calculator?
You just replace the capital T with the 160 and then plug that in. Right.
Well, they want you to use the intersect feature.
Well, and then you So you actually can plug that original equation in. Just
The second way to do it. And that is the second equation you want to put in there
160.
is 160, exactly.
And
then wherever they intersect will be the solution for t.
Mm-hmm.
You could do it the way you suggested also. I can put in 160 there and just solve it. Or put in 160 there and your inspire, and then you'd be looking for the zeros. If you did it your way, you'd still be looking for the intersection, but the intersection with the x-axis. Whereas if you do it this way, you're just looking for where the two lines, where this function and this function intersect. Sometimes you have to use the second method. For example, do I want to erase this yet? Yeah, I can erase some of it. If I have the following equation, how can I solve that?
For y equals sin x. Or no, x equals.
Yeah, there's no real algebraic way to solve it. I've got a combination of a polynomial, which is x, and a trig function, which is sine of x.
Mm-hmm.
I don't have any algebraic way of solving that. However, if I graph it, sine x looks like this, and y equal x looks like that. And so it's definitely got at least one solution there, and sine keeps doing this, so it's got another solution somewhere here, and it's got a third solution there. So sometimes when you have a mixture of functions, like one is a polynomial and the other is a trig, or one is a log and the other is a trig or something like that, frequently the only way you can solve it is by plotting both curves, and wherever they intersect is the solution.
Mm-hmm.
And I don't know if there's another way to do that. There must be. There must have been a way to solve that before we had graphing calculators, but I'm not sure what it would be. All right, let's erase all the ink. Trace the function for large values of time. What do you notice about y, the temperature? What would you expect?
Decreases over time.
To what?
0. Or to the room temperature.
Room temperature, 70.
Yeah.
Exactly. In other words, since it's minus 0.1 t, if I make t really, really big, then it's basically 1 over t. That thing approaches 0. And so the second part of that function is going to approach 0, and we're going to come down to 70 plus 0.
Mm-hmm.
And that's what you would expect. You certainly wouldn't expect it to cool off less than 70.
Mm-hmm.
All right. Have a look at the second problem.
The second one's on 2 pages.
Okay, and the first page was the one we just had open?
Mm-hmm.
Okay, Newton, the bottom, yeah, we're doing 14.
Mm-hmm.
Okay. So, are you looking at 14 on your own also?
Yes.
Okay, well, let me pull up the next page, and you can tell me these numbers. A thermometer reading 72 degrees is placed in a refrigerator where the temperature is a constant 38. So the thermometer.
72.
Uh-huh. Second.
And the constant's 38.
Yeah. So the thermometer is 72, the refrigerator is 38. Newton's law of cooling should hold, and we have to solve it. So what's our general?
30.
Let's write
that's
general
the
this way.
right. Oh, yeah.
If we write the general this way, we're less likely to forget it next time.
Mm-hmm.
Whoops, that's the t of the medium. This is the original minus the medium.
Yep.
And that's e to the minus kt. Never have quite understood why they put the minus sign in there. Because if I took the minus sign out, then when I figured out k, it would be a negative number instead of a positive number. And that would be fine. Then I would have my negative k. So maybe the minus sign tells you that it's always going to be cooling and it never is going to go up. I don't know. I'm not quite sure the purpose of why that says negative k. They have the same problem when they talk about exponential decay. When they talk about exponential decay, they stick a negative sign in front of the k also, which doesn't seem necessary if you go through the math. Seems like you wouldn't need that negative sign. But anyway, that's a problem for another time. So if the thermometer reads 60 after 2 minutes, what will it read after 7 minutes? How do I go about this?
We have to find the rate that it drops
I have
at.
to find k. In other words, k is what we don't know. Once we know k, we know all these other temperatures, but we need to find k. And the fact that they're telling us that it reads 60 after 2 minutes, well, we now have a number we can plug in for t, and we certainly can plug in all these other numbers, so we can calculate k. So what should I write? I'm going to write it over here on the left. Give myself some room.
The first T is the temperature, right? The constant.
Right. This is the final temperature.
Oh, it is.
Uh-huh.
Okay.
So
you're
if I want it to read 60, that's got to be 60. With me?
Mm-hmm.
Temperature of the medium is what?
60?
38. The temperature of the refrigerator, right? We're sticking
I forgot about
the
those two.
refrigerator that's at 38.
Yeah.
Plus,
and then it's
temperature of the original 72 minus 38. All times e to the minus k2. Now I'm going to erase this over here because it's in my way. E to the minus kt. Well,
and then 2.
there's 2. Yeah, right.
2.
And so now we can solve it. There's only one variable. So let's see. I got 22 equals 72 minus 38 is 34. So I'm going to have 22 divided by 34 equals e to the minus 2k. So natural log of both sides. So I got k equals that divided by minus 2.
Mm-hmm.
With a number for that?
Still doing it in the calculator.
Yeah, it won't even let you put that in there wrong, I guess, does it? Because as soon as you hit natural log key, it puts the parentheses in there already.
Yeah. Yes, I have to put that in.
Because that's an easy mistake to make in an older calculator. You could do natural log of 22 and then divide the whole thing by 34, which is not what you want to do. You want to take the natural log of 22 over 34.
So I got 0.217 or 0.218.
And you divided by the minus 2?
Yep.
Okay. So now our equation reads what?
Oh, so you got your temperature. Yeah. So just K is the 2.18. So for
Well,
this is
we can fill in the other numbers. In other words, our specific model here, the temperature of the medium is 38 always. And the rest of it's the same too. 72 minus 38 times e to the minus 2.18 t. So there is our specific equation for this model. Now we can answer most every question they want to ask us. In other words, once you've solved for k, then you can apply this equation to anything.
Yep.
Okay? So what will it read after 7 minutes?
Let me put that in real quick.
Well, just give me the equation first.
Oh, you got 38 plus, and then parentheses 72 minus 38, and then out of the parentheses e to the power of negative 0.218 times 7.
Okay.
So I got 45.
Okay. So it'll read 45 degrees after 7 minutes?
Yes.
In other words, T of 7 is 45 degrees. Interesting. D has that answer. I guess they're showing us that we can do it algebraically or using logs, or we can do it by graphing it. How long will it take before the thermostat reads 39? So give me the equation I'm going to use for that.
It's just so it's, what is it, 39 degrees, right? So 39 equals 38 plus, in the parentheses, that's 72 minus 38, and out of it, it's e to the power of negative 0.218 t.
And this time we're solving for that t. Okay. So subtract the 38, I get 1. Divide by 24, I get this. Take the natural log of both sides. As you can see, you're always taking the natural log of a fraction on the left, dividing it by minus 2.18, and that's going to equal t.
14.7.
Okay. Minutes. And incidentally, the units on t can be anything. They don't have to be minutes. They can be hours, seconds, whatever. Whatever unit you use when you solve for k, that's the unit you got to stick with, though. In other words, this k of minus 2.18 is based on a t that is in minutes. So if t were in hours, I wouldn't have the same value for k. And that would be fine. But then I'd have to make everything in hours. All right, so using the graphing utility, you can graph that, and what you'd graph is this one, using 24 here, or 34. Did my math wrong. That means that 2.18 is not correct. I mean, 14.7 minutes is not correct. What's the natural log of 1 over 34, all divided by minus 2.18? Made a mistake.
Oh, it was 0.214. 0.218, not 2.18. 34 divided by negative.
We're taking the natural log of 1 divided by 34.
Yeah, I got, and then divide that by negative 0.218, which I got 6.
Negative 2.18.
Oh, no, it's 0.2.
Oh, it's 0.218.
Mm-hmm.
Okay, what does that give you?
I got 16.17.
Okay. That answer certainly makes more sense. In other words, if it falls to 60 degrees in 2 minutes, I could see it taking 16 minutes to fall all the way to 39 degrees. Use the intersect to determine the time needed to elapse before the thermometer reads 45 degrees. Again, if you're using the intersect feature, then you're going to graph that equation, you're going to graph another function that equals 45, and wherever the twain shall meet, that's your answer.
Mm-hmm.
Trace the function for large values of time. What do you notice about y, the temperature? Again, it's going to drift towards your median. In other words, here's what happens. As t gets really big, this thing goes to 0.
Mm-hmm.
Because it's a negative exponent. So it's really 1 over e. If I took 1 over e to 1,000,000, that would basically be 0. Wiping out that whole figure and leaving you with the temperature of the medium.
Mm-hmm.
It always goes to the temperature of the medium as t goes big. All right. I think you're probably good to go on these.
Mm-hmm.
They all kind of work the same. You have to figure out k, and then you can get a specific equation and answer all of their questions.
Mm-hmm.
But first you have to figure out k, and you can do that by their initial conditions that they give you. The fact that they tell you it goes to 60 in 2 minutes is what allows you to figure out k. All right, Sam?
Thank you.
You're welcome. Talk to you next time.
Mm-hmm.